Hi everyone. Great to be here. Actually, I need to correct you one. I'm actually a manager of a development team and not a research scientist at Meta. So I expect some more manager type and high level view of what we believe the needs are for display developments. Actually, what I want to show you is what the display development status at Meta is based on micro LEDs, but mainly focusing on what are the development directions, where do we see gaps in micro LEDs still going forward. The micro LED team is actually located in Cork. This is in Ireland, in Europe. This morning when I crossed one of the bridges, actually it felt like being in Ireland, very windy, so it's very much the same here, felt a bit like home. Okay, when we look at the typical systems we have, let's see. Here we are. So we have the, we talked about already about waveguides, input grating, input in-coupler grating, out-coupler grating, and the display projector here with the emissive display. We see immediately the problem. We want to fight the sun outside, so inherently very high brightness is needed. But also what's needed is understanding how all the system interactions actually work and how this works with the perceptual system of humans. So I'm glad that we talked about that already earlier on. Actually, if you look at luminance, luminance levels required out the current display technologies available, LCD, OLED, but also micro LED. There are a lot of progress in these areas, but we are speaking about 1,000, 2,000, maybe 10 and 20,000 nits brightness. And what we need for any AR system based on waveguides is like 3 orders of magnitude above that. So you need a really different technology to go there. And also resolution is a bit higher compared to what we see in OLED right now. I think from our perspective there were 2 real advancements related to micro LED displays in the last year and maybe less. So one is we talked about that already, the announcement of Orion, which is the first implementation of a wide field of view AR glasses, where it actually include a micro LED light engine. So you see here, probably you've seen this, and maybe, I don't know, Ivan, if you had the chance to wear these glasses. It's really impressive, this wide field of view that you have. That's also based on silicon carbide waveguides. Still, there are a lot of things we need to improve, but it's a kind of a time machine. It can show you what's possible, what can become possible in the future with these kind of technologies. And particularly with the AI now embedded into these systems, when you have actually a display, it can show you things, can navigate you, can show you explanations to things based on a display, which right now is possible through speech, of course. The second one, we've actually announced with one of our partners, Plessey Semiconductors. It's a fab in UK, that we believe they achieved the brightest red active matrix display, so on an active backplane driven display, below 5 micron pitch, roughly 6 meganits brightness. So we discussed this earlier. Red is probably the largest challenge from a micro LED perspective. You have to fight surface losses, high current density needed here. And this is a kind of a breakthrough that enabled also Orion and the brightness levels we've seen in Orion. When you look at from a very high level on the current display technologies for AR, when you see majority of the products you may see out in the market are cost-based, but we are seeing right now a transition to micro LED display engines. So micro LEDs are becoming in a position that they can take over and are deployed in more and more products. There's obviously a future, and that's the question: what is the future? Maybe is it a laser-based system? Is it a different type of waveguide? I think this is really open research going on right now. But what I want to talk with you right now is what actually can help to increase the market adoption of micro LED. So what's still needed to go forward to improve performance and work on the issues right now. And you've seen, I've just used the diagram that Leo just showed in his presentation. So also for micro LEDs and the display engine, you have a very similar trade space. You have optical performance, you have weight, form factor, cost, later on manufacturability, but also the maturity of the technology is super important here, right? And initially, it's clear you need to deliver on the highest priority requirements, right? So high brightness, high resolution, high efficiency. That's everything that mattered almost in the last couple of years for us. So we've been driving to improve brightness, efficiency, and resolution, but that's not enough. So when you go forward, still further improvements in efficiency is needed, mainly wall plug efficiency. And in the system design, you have always, there's a trade, and if you come up with higher efficiencies, unfortunately the system takes a bit away from your power budget, and you have to continue to improve. That's a typical system development. But the next thing that's really coming up is form factor. Form factor is driving these kind of things. When you look at the Orion demonstrations, it's really already a nice form factor device, but it's still a bit bulky. So we want to have it more acceptable, more lightweight. So we have to improve on that, and that's really mainly driven by form factor needs to reduce, but also PPD and field of view need to increase at the same time. So here you have a problem. You need to find a good solution. And then obviously the other things are coming into play as well. So cost, when you think about millions of devices that we want to deploy ultimately, cost is a big topic, but also manufacturability. Can you manufacture these kind of very complex, very different display engines? All right. I would like to show you kind of two examples where we think improvement is needed. And we've seen this or heard about this quantum color conversion concept already. I mean, this would be ideal. You have a blue micro LED at the bottom. You have a green and a red quantum dot color conversion layer. You have beam shaping optics. You can pattern these quantum dots very easily. So you have the advantage of a monolithic integrated design. It will reduce costs. Inkjet printing could be potentially very cost efficient. You can easily tune the color with that. But what we see right now, it's actually with the current technologies, it's not system viable yet. And I'll show you why this is the case. So first problem, beam collimation. So for a waveguide-based system, you need a narrow emission cone. And inherently, these, so you can only couple into the waveguide over a narrow acceptance cone. But the emission of the quantum dots is typically a Lambertian emitter, right? So lens design is restricted by the neighboring pixels. So you have a neighboring pixel, you can't have a huge lens on top of each pixel, it doesn't work. So in the solution space, a method to produce a collimated emission profile directly from the quantum dot, or a quantum dot materials with directional emission. Apologies, it's my phone. Maybe my wife. Oh, back to that. Okay. All right, next one, low color conversion efficiency for quantum dots. So often you have a low absorbance of the incident light. You can add material, essentially. You're adding path lengths of scattering material. But here's a problem with mainly multiple reabsorption and emission events, which reduce the quantum yield of your structure. So here, thinking about increasing quantum dot absorption at the pump wavelengths, engineering quantum dots with a larger Stokes shift that prevent this reabsorption, re-emission event would be very much needed. And last but not least, reliability, right? So commercially available quantum dot OLED TVs operating with very different fluxes in a range of below 1 watt per square centimeters. What we are looking for, it's definitely way above 5 watt per square centimeter in terms of backlight flux. And for this, we see right now still a very poor reliability for the materials. So increased operating stability of the quantum dots to a high incident flux is key to make this technology viable. Also, incorporate reliability testing into academic research could be helpful to make these material choices early on. So overall, I think there's a good value proposition for quantum dot color conversion RGB AR displays. But as I said, low beam collimation, low color conversion, and reliability are the main problems that have to be addressed here. And this could be overcome with new nanomaterials and developments. The last topic I wanted to mention is heterogeneous integration to enable future AR glasses. I've picked here an example of a monolithic integrated OLED based on with an IXO TFT pixel circuit and a silicon CMOS driver beneath. It's a very, very small form factor for those kind of devices. And the same you could imagine in RGB micro LEDs, based on 3-nitride blue-green, maybe 3-phosphide red, and a silicon CMOS. We heard already about the company JBD, so they've showcased something like that. That has still very likely issues, but this could show a path forward to integrate things further into a smaller form factor and also more costly solution. But also I would like to mention wafer level optics. So we have a lot of optics in the display assembly, and integrating some of the optics on top of the micro LED array could be very beneficial from system perspective. So this could be chip to wafer bonding, wafer reconstitution approaches. There are a lot of approaches that could be beneficial for that, and a lot of opportunities for integration techniques for the next generation AR displays. Okay, with that I would like to close. I wanted to show you that AR displays offer new opportunities for contextual AI, but also there are continuous improvements needed across many axes to get us where we want to be. Thank you.
Great, thank you. Yeah, so I was just kind of curious or whatnot. It was reported that Orion used kind of an off-the-shelf product by JBD for their full-colored display there, utilizing kind of a 3-panel approach. So does Meta kind of see the future more in terms of monolithic, it seems like? Because you hinted more at quantum dots for optical down conversion, or JBD's solution of kind of a stacked micro-LED approach?
I think that's it's not too clear what the future here is. I think monolithic definitely has a lot of potential advantages, but you have to also consider if you stack them laterally, for example, white pixel pitch increases, and that creates challenges. So I think it's not really clear. There are some options that we are working in and that you have to trade off essentially. There also, I think we haven't really disclosed for Orion what kind of displays have been used, but there are multiple versions, multiple different embodiments, I would say.
Thank you very much, great talk. I'm curious about what's your solution for the free AC problem, versions and accommodation conflict. Do you have any solution for that issue?
Good question. I mean, I'm not the most expert in this field, but we have in our team in Meta and Reality Labs, we have a whole perceptual science team who's actually dealing with that. And I think what's very important is user studies. So we rely a lot on user studies. We're trying to build demos early on, and we're trying to show them to people. And that's actually what also the importance of Orion was to finish this first a product as a time machine to show to people to get feedback when people wear this on a daily basis and give feedback how this feels, and if you get motion sickness or if you don't have any issues with that. I think it's also an ongoing topic.